Hello, in this video I'm going to continue with the NSAA from 2023, so that's the Natural Sciences Admissions Assessment. In the previous video I went through the 20 maths questions, so these are the rapid fire multiple choice questions, 20 in half an hour. In this video I'm going to go through the physics questions. Once again I'll try and point out a few tips maybe for getting some extra questions in if you're struggling with time. So I'm going to go through these a little bit slower than I would do if I was going at full speed. Hopefully I'll still scrape them into the half an hour. The physics questions I find take longer than the maths questions because there's more to read. There's more text in the questions. So there's more of a case for skipping the long-winded ones if you know you're not going to get all 20 in, or at least skipping them and then coming back to what you could maybe do at the end. Many of the tips are going to be much the same as for the maths section. Yeah, you want to have fluent algebra, fluent number manipulation, so you don't have to write down everything when you're going through the answers. You know, you can skip out a few lines, get to that answer a little bit quicker because you're not having to spend so much time with a pen. So with that in mind, I'm going to set off the stopwatch and see how I get on. Right, question 21. An object of mass m, weight w, so the usual write it out as you go, so you don't have to double read, is on the moon. Moon has no atmosphere. Object is released from rest at a height h above the surface of the moon. Which expression gives the speed of the object as it reaches the surface? So our work done, our WH, that's the energy transferred into kinetic energy from the potential energy. So 2WH over m square rooted. So G. Banked some time on that first one. Question 22. Spaceship, mass 10,000 kilograms. Moving at 2 meters per second relative to a space station. Spaceship is captured by a robotic arm attached to the space station, brought to rest by a force of 1,000 newtons. So opposite direction to the speed of it. How far will the spaceship move in its initial direction relative to the space station while the force is being applied? So we've got an F equals ma, so our acceleration is going to be the force 1,000 divided by 10,000. So we've got a deceleration 0.1 meters per second squared, so 20 seconds to stop it, at an average speed of 1 meters per second, so 20 meters. This one, if you're still over reliant on SUVAT, then try and wean yourself off of that. If you've watched my videos on kinematics and dynamics, you'll know I'm no fan of SUVAT, and in these questions it's just going to slow you down. SUVAT dulls the brain really, and it makes it harder to answer these questions. So try and wean yourself off those if that's what you're still using. Question 23. A heater is connected in series. Okay, that's just describing the circuit. Variable resistor is adjusted till the reading on the ammeter, 0.5 amp, we've got through there. Resistance of the heater is 8 ohms. How much energy is converted to thermal energy in 5 minutes? Well, I'm assuming they mean thermal energy in the heater. Can't really see what else we're going to do there. It's going to be an I squared R. So that's our power, 1/4 of 8. And then we've got to multiply that by 5 minutes. So we've got 10 times 60 is 600. So quick work on the numbers. So it did give us easy numbers. So that was something. 24. Circuit setup as shown. All 3 resistors identical. When the switch is open, we're getting 1 amp on the ammeter and 1 watt from the battery. Switch is then closed. What's the new reading on the ammeter? Well, it's not going to change because the potential difference hasn't. What is the new power transferred? So we're still getting 1 amp, and we're going to get 0.5 amp through here because it's double the resistance. So we're going to get 2/4 watt increases. So we're going to go to 1.5 watts. Have we got that somewhere? Yes, so F. So I haven't made a mess up, so that's good. Similarly to SUVAT for this one, if you're still just Kirchhoff law, Kirchhoff law, Kirchhoff law when you're looking at circuits, then you could probably be doing better with that. So you could always watch some of my videos on circuit analysis. You know, start with your PDs, then go to your currents, then go to your wattage on simple circuits like this. But if we're not changing the PD between 2 points, we're not going to be changing that current. And then, you know, our PDs are going in proportion to resistances and inversely proportional to the resistances for the current. So if we've got double the resistance, we're going to have half the current. So these sort of things we're going to be looking at. Right, so yeah, just don't get over reliant on your mechanistic ways of answering these questions. Don't get too reliant on Suvat or Kirchhoff's laws when you can get a bit more insight into how to answer these things. Anyway, question 25. Car travels for a total time of 20 seconds, and that's split into, right, this is like a graph one, isn't it? It's split into t at 5, and then the rest of it at 10. Average speed is 8.5. So what is t? So we're going to have 20 times 8.5. That's our total distance traveled. It's going to be 5t plus 10 times 20 minus t. So that is 200 minus 5t, and that is 170. So we've got that t is 6. So quick maths on that one. Right, a spring is initially unstretched. Force F, extension X, energy E. That's told us nothing in there. Graph shows that. Okay, it's just all about the graph. What is F? So we want to get F. So F is Kx, and we've got a half Kx squared is E. So we want to do then, so Kx. So we've got to multiply this thing then, haven't we? Well, we need to get K, is what I'm saying, really. So we will need to do 2E divided by X squared multiplied by X. Get rid of those. 2E over X, 0.015 times 2. All right, so 0.03. And then X. Right, what we got? Oh, that's centimeters squared. That's newtons, right? So that's going to be 0.05 then if we take it to centimeters. So 3/5, which is B. Okay, so that was okay. 27. That's helium-3. Well, it is indeed. And we've got some element X. It's got double the nuclear charge, 4 times the mass. Then it decays by a single beta emission. So that's going to put the 4 to a 5, and that is then Z. Okay. Oh, right, and that's all they want to know. Right, E. Right, and that's certainly banks some time. A solid cylindrical metal bar has got cross-sectional area 12 and volume 180. This is all in centimetres. Oh, we got centimetres there, so that's good. And it rests on a horizontal surface on one of its faces. All right, so it's that way up. And the pressure on the surface, 0.45. That is our force over area. The area is 12. We want the density. So that's going to be rho times V times G. And we need that. And that is 180. Okay, so 12s into 180. That is going to be 15. Right, so we've got that times, divide by 15, sorry. And then we've also got a 10 divided by 150. Nothing like those answers. Oh, they got it in grams, and this is kilograms. So we need to multiply that by 1,000. So that's going to be 450 over 150. So 3. Okay, right. That was fine. Keep an eye on your units. 29. I mean, look at the length of this. So this might be one to skip if you're thinking you're going to be pushed to time. A ray of light is directed horizontally between two plane mirrors, both at 45 degrees. Right, so that's just the picture. We're coming out parallel to how we went in. Mirror X, the bottom one, is now moved that way. Right, it's now at an angle theta. What direction through what angle should mirror Y be rotated for the ray to still be horizontal and travelling to the right? Right, so we still want to be coming out that way. So we're coming on to here. So that's at theta. Coming off of it, that's at theta. We now need to hit something that's going to take it along that way. So boom, 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 that's 2 theta that we've got there. So we need to split that difference, have it going like that. So that'll be theta, that'll be theta. So what have I actually done? That started off at 45 degrees. What on earth is it at now? Yeah, what is it at now? So that's theta there. So if that was 90 degrees, then we've got a theta there. So we've gone from, my picture's so confusing now, I can't see what I'm doing. So I've got that's theta, and we've got, so our angle, what angle am I looking for? This angle is theta. So we've gone from 45 degrees to theta degrees, and we've rotated it that way. So we're rotating clockwise. So that's a start. And we need to go through, well, we're taking off 45 and adding on theta. So it's going to be 45 minus theta is what we're going to be doing clockwise. So that is E. Okay, that was a fiddly one. So a good one to have skipped if you were going to be wanting to do so. 30 anyway, 2 pure samples of X and Y radioactive, half-life of 2 days and 3 days. They both decay in a single step. Initially we've got twice as many X as Y. Okay, so let's just pick some numbers. Powers of 2 should be better, but I'd still just find it easier dealing with hundreds. After how many days are they going to be equal to each other? So, well, we're going to get 2, 4, 6, 8. It's going to go 150, 25. Well, that's going to get to 25 after 2, isn't it? So 6 days. Okay, that was a bit of an easy one. But that's a bit like the one we had in the maths set of questions with the salaries of the sports coach and all that. You don't have to keep everything with ratios here or was it percentages in that maths question. You can pick your own numbers. It just makes it a bit easier to work through. 2 stones are held at rest at the same height at the top of a cliff. One stone is released, falls freely under gravity. Time t later, the other stone is released and falls. Which graph shows how the vertical distance separating the stones varies with time from the moment the first stone is released? Right, well, when one of them is falling and the other one isn't, you're going to get that because that's our, well, square of the distance goes as a parabola, doesn't it? If we've got a constant acceleration. So we need that up to time t. So it could be A, not B, then not C, not D, not E, not F. I mean, they haven't left much, have they? A big G and T are fine. So A, G, G and T, G and H. A, G and H are all fine. And then we're releasing the other one. Well, A is still going to be pulling, the first one is still going to be pulling away because it's moving faster and they're both accelerating at the same. So it has to keep going up. So it's not going to be G and it's not going to go flat either, is it? So it's not going to be H. I mean, the only one that's even vaguely possible is A. So they haven't given us very many options there. So process of deduction there, a bit like those graph questions you get in the MAT. You don't have to understand every part of all of these, or even not be able to work out exactly what it would look like. You just go process of elimination. Right, 32 then. A large flat metal plate is coated, this looks like another one to skip anyway, coated on one side with a layer of thermally insulating material, same thickness A as the metal plate. Right, the uninsulated top surface is at T1, so that's a constant T1. Bottom surface is at a constant lower temperature, T2. So this is cold, this is hot, or at least cooler and warmer. Systems in equilibrium, diagram shows this arrangement. Right, that's fine. Which graph could show how the temperature varies with distance from the top surface of the metal plate to the bottom surface of the insulating material? So we know it has to be colder. Right, so they're going top to bottom is left to right. So it has to be colder on the right. How many have we got? We've got 5 graphs here, right? So they're all going off to the side. It has to meet in the middle if it's in equilibrium. At the boundary, they've got to be the same as each other. So, okay, you've sort of got a step change there for E. But they're insulating and non-insulating. So we're going to get a gradient. We're going to get a temperature gradient between these things, and it's going to vary more, where you're going to have less flow of the heat in the insulating material. So you're going to get a bigger temperature difference in the insulating material because it's protecting the cold surface from the warmer plate. So you're going to get a steeper line in, so you're going to get A. Like you're going to get a bigger change in the insulated bit than you are in the uninsulated bit. So, the uninsulated bit is conducting better, so it's going to have a more even temperature. So it's going to be A. It certainly can't be any of the other ones. Okay, another fiddly one. So you might have skipped 31 and 32 because they were quite long questions. Right, 33. 10 grams of ice at 0 degrees, 20 grams of liquid at 30 degrees. Mix them together in thermal equilibrium. What temperature is the mixture? Right, so with these ones, this reminds me, well, it's obviously a completely different type of question, but the one we had in the maths with the surface area and the volume thing, where you've got, this is the technique that I use. So with these ones, go-to technique for me anyway is how much energy have we added from everything being at the lowest temperature. So say we had 30 grams of ice and then we wanted to get to this situation. How much energy have we put in? How much energy have we got to play with? So for 30 grams of ice, we're taking 20 of it. We've got to melt 20 grams. So that's going to be 20 times the 330 in order to melt it. And then we've got that 20 grams we need to take up to 30 degrees at that specific heat capacity. So that's how much energy we've put in. And that's coming out as what we got here. So that's 126 we're adding on. So 456 times 20. That's our energy. Now, if we've then got 30 grams of it all, to melt it, we're going to have to do 30 times 330. That's the energy to melt. Then we'll see what we got left over. So that is 20 times 1.5. So that is 20 times 1.5 of this. So we can add on 165. So 496. All right, so we can't even melt it with the energy that we've got. So it's still going to be frozen. It's still going to be at B. But yeah, go-to method certainly helps. Voltage output of a power station is stepped up using a transformer. Okay, we've got 300 to 1500 turns, so we're putting the voltage up by 5. Step down transformer reduces the voltage, so that's going to the cables. Then we're stepping down to 33,000 in town, and that's 1500 amps. We've got 450 amps here. So that means our voltage there. So we want the voltage output of the power station. Right, okay. So we need the voltage over here. So that's going to be a fifth of whatever we're getting in the cables. The cables are going to be 1500 over 450 times that. That's what we've got in the cables, and we want a fifth of this. So get rid of that, get rid of that. 30 over 45, so 2/3 of 33,000 C. So that was just straight number manipulation and being secure on that, providing you can you're good enough with your transformers of how they actually operate. But again, number manipulation, just as we had on the maths section, that's what's saving you the time. Physicist introduces a thin piece of glass into the path of a laser beam, okay, to delay it. We've got wavelength L. While the beam is inside the glass, it completes 10 more oscillations. So compared to in the air. So if we've got X oscillations there, X plus 10 oscillations there. Speed of light in air is C, and in the glass is 2/3 of C. So that means we're going to get 2/3 of L for our wavelength in the glass because the frequency won't change. It's only the wavelength and the speed that's going to be changing. So we need to get the thickness of the glass. The thickness of the glass is going to be, when the language of this question is going to be X times L. It's the number of cycles times the wavelength. So that's what we want to work out. Okay. And that's why there's L in all of the answers here. So we're saying then that X times L for this bit is going to be equal to X plus 10 times 2/3 of L. And we want XL, so I just want this. So I'm going to be taking off 2/3 of XL. So XL over 3 deals with that. And that's going to be 20 over 3. So XL is going to be 20L, which is E. Okay, that was a sneaky little question. Transverse wave with an amplitude of 3 centimeters travels along a stretched string. The wave has frequency of 12 hertz and it's got a wavelength of 1/4 meter. What is the average speed of a particle in the string? Right, so we're not looking at the speed of a wave, we've got a particle. So in 2 seconds, we're doing 24 cycles. Each cycle is 3, 6, 9, 12. So 12, that is going to be, well, 288, 2 lots of 12 squared. So that's how far in centimeters is traveled in 2 seconds. So it's going to be 144 centimeters per second. Bit of a red herring with the wavelength thrown in, but not much of a red herring. 37, copper ring, small gap XY, rests in a uniform horizontal magnetic field. Okay, ring lies in the plane of the page and the magnetic field is left to right as shown. Right, so there's nothing of interest there. Voltage is applied across XY. X is positive, Y is negative. So we've got current going that way. What's the motion of the ring? Right, so let's look at the extreme points then, where we've got the current is perpendicular to the field, and then do the right hand slap rule. What's this? Assuming the mechanism supporting the ring allows the ring to move freely. Okay, whatever. So right hand slap rule, we've got fingers for the field lines, we've got our thumb going downwards, so that's a bit of a contorted one. Force out of the screen on the left and into the screen on the right. So this is coming out, that's going in, so it's going to be spinning around. So we've got this axis of rotation and it's going to spin that way. So what we've got, ring moves, ring moves, ring moves. No, we want rotates. So bottom 4 rotates in an axis perpendicular to the plane of the page. No, it certainly doesn't do that. So in the plane of the page, yes, that's good. Parallel to the field, perpendicular fields. Okay, so H. So that was fine. Not a lot to do there, just a lot to read again. Question 38. A battery and 2 resistors X and Y are connected in series. Okay, power transferred by the battery, you've got 6 watts up here. Voltage across Y is, oh, resistance of X, I nearly missed that one, that's 10 ohms. Voltage across Y is 4 volts. What's the current? Right, okay, so we've got current I there, we've got current I here, current I there. We've got a voltage V there and a resistance R there. So there's not much insight we're going to get into this circuit. We need to get I. So that's what we want. So we're just going to have to set up 3 simultaneous equations. So we can do a V equals IR on that. So 4 is I times R. Then we can do our, well, let's use the wattage. So 6 is going to be the current multiplied by the EMF, which is a 4 plus V. So that's good. So yeah, put the EMF there. So really we've got 4 equations. You know what I'm saying? The E is 4 plus V, but just skipping that bit out, don't really need to spend the time. And then we have to do something with the 10. Well, it's not going to be the subject of the equation, is it? So, well, I can do a V equals IR on that as well, could I? Yeah, I suppose I could do. So I could say that V is 10 times I on all of this. So now I've just got to stick all of this together. So what am I going to be? And I want to get I. So V is, okay, so I've got 10I here. So I can just replace that bit. And then, actually, I don't need anything else, do I? No. Actually, I didn't need as many equations as all of this by the look of it. So I've got that 6 is 4I plus 10I squared. 3, 2, 5. I is going to be minus 2. I have to be plus on the square root. So that'll be 4. And then it will be plus 3 20s. Plus 60. Excellent. Over 10. So that is -2 plus 8, so 6/10, 3/5 B. Okay, so a lot of messing around on that one. 2 questions to go. So 39, a cubic block of wood, side L, floats in water, top face horizontal. Okay, so it's just floating without being disturbed. Block is displaced downwards by L/10, so that's side L. We're pushing it down an extra tenth, then it's released. The density of the wood is 0.8 grams per centimetre cubed. Water is 1 gram per centimetre cubed. Right, so we're already 4/5 under. And then we push it another tenth under. What is the initial acceleration of the block after it is released? So we've got our mg going downwards. Let's just say, let's make this easier and make it a meter cubed. So we've got 800 kilograms of wood, and we're going to have 1,000 kilograms of water. Let's go with that then. So, you know, it doesn't, we're still going to get the same thing because we're going to be dividing by this mass when we get to the end. So let's just deal with some sensible numbers. We want the acceleration. That's going to be the force over the mass. So I've said that the mass is going to be 800. The force that we're going to be getting then, so upwards, we've now got 9/10 of this water. So that's going to be 900 is our kilograms, and then we're going to have the G for the up thrust. So that's our upwards force, but our weight is 800 G. So we got 100 G, and they've given us that. So that's 1,000 over 800. So 1 1/4, which is C. Right, okay, that one's okay. You might have seen that sort of question before, but a lot of people struggle with that the first time they see it, these sort of upthrust questions. But again, get some sensible numbers, because we know that the m's are going to end up cancelling on these things. So just pick out a weight. You don't have to deal with L's all the time. You can just throw those L's away because they get removed if you're doing it all with the algebra. So it's like going back to the sports coach and the radioactivity again. Pick friendly numbers. Right, question 40. So a diver at the bottom of a lake of depth D fills a syringe with an ideal gas, seals a nozzle. Piston remains free to move. The volume of the gas at the bottom of the lake, so this is 90 centimeters cubed at a depth of D. Okay. Then they go to the surface. Temperature doesn't change. Okay, so we've got PV as a constant. And the surface, at the surface, the syringe is at atmospheric pressure, and the volume is now 720 centimeter cubed. Okay, so that is at depth 0. Okay, and we want to get the volume of the gas at a depth of D over 2. Right, okay, so we need to work out what the change is in pressure from the surface to D, and then halve that and work it out from there. Right, so we've got the P0 times 720 is PD times 90. So we've got that PD is going to be equal to, what's that, 8 times P0. So the change in pressure going down to PD is going to be 7P0. Okay, so our pressure at D over 2 is going to be half of that change in pressure. So it's going to be a P0 plus half of that change. So P0 plus 7 over 2 P0. So that's 9 over 2 P0. So that's our pressure at half the depth. And then we have to do the volume at D over 2. So that is going to be P0 times V0, so 720, divided by PD over 2. So divided by 9 over 2 P0. So they're going to cancel. So I'm going to get 2 lots of 720, so 1440, divided by 9. So what is that? That is going to be 160. Is that coming out 160? I'm going to get 1 and then yeah, 54, which is another 6. So yeah, it comes out A. Right, I always find those ones require quite a lot of thought, because you always have to factor in this bit at the start. You know, you start with a P0, you go to a PD. So when you're at PD, you've got your initial pressure plus the change in the pressure. So you always have to keep that P0 in the calculation when you work out the pressure at half the depth. You can't just say, oh, well, it's half the pressure at depth D, because you have to, you know, sort of baseline everything off of that P0. So that was quite, in fact, the last 2 questions were quite long-winded. So yeah, you can see how it takes a lot longer to do the physics questions. But just quickly skimming through these, I mean, you've got 2 long-winded ones at the end. Then, okay, that one was a bit quicker. That one was quite quick. But you still got a fair few quick ones. I mean, if you skipped out, say, the last 2, maybe the one with a laser, perhaps that one, and that, well, that one wasn't too bad. I'd say there's 5 quite long ones that we had. The one with the mirrors, this one, the one with that surface, so those 3 and the last 2. 5 long ones. Maybe just don't think about those ones at all if you're really going to be up against it for time. Because those first 8 were pretty quick. So you can bank some time there, that's for sure. But in terms of the actual working out and how to save time, there's less time, I think, to be saved here on these physics questions than there are on the maths questions. And the advice is much the same. Write out as little as possible, be fluent on your numbers and be fluent on your algebra. So there's probably less to be gleaned, maybe, in this video than there was in the maths video. Oh, I suppose with the exception of don't be over-reliant on Kirchhoff's laws. Don't be over-reliant on SUVAT in particular. If you're doing SUVAT on any rapid-fire question, then there's going to be a better way of doing it. You know, spend more time with your kinematics and your dynamics so you don't have to rely on it. And that could easily save you a minute just for that. But there you go. Anyway, it's gone through that paper. I don't find these rapid fire papers very interesting, really. The questions don't have that much substance to them. I know we had a couple of meteor ones towards the end of this physics block, but there's not much to get excited about these. You know, so I'm not going to be doing videos on every NJA and every NSAA paper and all the other ESAT variations. It's just not interesting enough, these questions. They're just nowhere near as interesting. So I don't really fancy doing videos on these, because you can work out how to answer these questions given the time. So I think just focusing a bit on how to go quicker is all it really needs in these videos. So that's wrapped up this paper anyway for NSAA.